We are continuing on here our journey into 14. Last time we went over again weak acid problems, which are basically Ka type problems, and weak base problems, which are really Kb type problems. They're really just like any other sort of equilibrium problem. Except that in the end, oftentimes we are interested in the actual pH of the solution at that point. So we do go through our ice table like normal. We do solve for X. In the case of solving for X in a Ka situation, that X will equal the H plus concentration, which means you could go right into sort of the pH equation at the end of the ice table. In the case of the Kb, if you write the equation correctly, which hopefully we should be doing, you will have hydroxide there in your ice table, which means when you do solve for X, though, in that case, that is actually the hydroxide concentration, which means you do have to go POH first and then to the pH in terms of that. We could do our normal assumptions and all those kind of things, and we could get to our pH. We also talked about, I think, comparing sort of acid strength. Again, depending on the type of acid you're dealing with. If it's an acid that does not contain oxygen, the sort of overwhelmingly thing that you look at is what is referred to as bond enthalpy or bond strength. The stronger the bond enthalpy, the harder it is for that H basically to come off. And essentially, it's usually like an H there. So we really want to break that bond. So again, the larger the bond enthalpy, that H is going to pretty much hang on a lot easier, is not going to come off, and thus it would be a much weaker acid than something that has a smaller bond energy, which means we could break this bond relatively easy, allowing that H basically to come off. When we're dealing with acids that contain oxygen, which are sometimes referred to as oxyacids, it sort of depends on the situation. If you have a central atom where basically they both share the same oxidation number or oxidation state, we then look at electronegativity. So when we got oxygen involved, we look at electronegativity of that central atom. The one that is more electronegative will be the stronger acid, as it will weaken that bond that has the H on it and allow it to come off a lot easier. Again, if we, when they have the same oxidation number. When we do have a central atom that has different oxidation numbers, so perhaps like we saw the same element in different acids, but they have different oxidation numbers, we do look at the oxidation number when we do have different central atoms. Or actually no, same oxidation number, when there is a difference in the oxidation number. And same idea there, the more positive sort of oxidation number or larger positive oxidation number on that central atom will once again weaken that bond and allow the H plus to come off quicker and be more, a much stronger acid. We finished up talking last time and this morning about salts. So salts, right, again, are generated from a reaction of an acid and a base. And as we talked about, you know, it's really important to think about really where the salt comes from and understanding the opposite relationship. Again, if your salt comes from something that is a strong acid or base, then the salt will be what is considered a neutral salt. And really what that means is it will not go through hydrolysis. Because it comes from a strong acid or base, it's relatively weak, which means there'll be no reaction really with water. It's only when you got something that really does come from a weak acid or base that the salt partner there will be relatively strong, and it will go through hydrolysis. And as we talked about this morning and last time, basically it's going to result in basically two things happening, one of two things usually. Either the salt will donate the H plus over, that will again result in H3O plus being formed on the product side, which we again would expect it to be an acidic solution, or the opposite there is that the salt will actually accept that H plus from the water, The result of that there is you're going to produce hydroxide, which will make it a basic solution. And as we talked about, it's important to know that I should be using a Ka there. And if this is the situation, I definitely should be using a Kb there. Any questions on any of that stuff we talked about last time? All right, so we looked at an example, I think, last time. So let's take a look at an example here where we actually need to do a calculation. So consider a 0.3 molar solution of sodium fluoride. The Ka value here for HF is 7.2 times 10 to the minus 4. So in this situation, if we wanted to predict what the pH is of this solution, this actually doesn't ask for anything here. That would be a great question. What is the pH there? So if we want to know, was it? Oh, maybe I do need to do that. Let me see. There you go there. Oh, there it is. All right, it's a better question now if I clicked, I suppose. All right. So we're looking for obviously what is the pH here, and in this situation, we do need to do an ice table, but we also want to look at the salt and sort of think about, again, what part of it will go through hydrolysis, if any part. So when we look at something like sodium fluoride, it is going to break apart into a sodium ion and a fluoride ion. So really our first question is, when we analyze our two components here, will any of those continue to react with water? So let's start with the sodium. Will the sodium go through hydrolysis? It will not. So as we've talked about, pretty much anything that comes from group 1 or group 2 on the periodic table will not go through hydrolysis. Again, really because those are our strong bases come from there, right? Like sodium hydroxide is most likely where this sodium sort of originated from. So we don't have to worry about that. Now we want to think about the F minus. Will the F minus go through hydrolysis? So this is also where we can look at the question, and it does give us a lot of really great information that could help us with answering these things. First off, where does F minus come from? It does come from HF, which I actually see here in my problem, right? And it actually does come in from HF. The other thing that I see with my HF that's given to me in the problem is there's a Ka value for it. That tells me my HF is what type of acid? It is a weak acid, right? Because it's only weak acids that have Ka values associated with it. So sometimes the problem gives you a lot of really helpful information. Sometimes people just kind of go right by all that stuff. So, you can look at the problem here and actually get a lot of that information. So we actually know that this salt really kind of came from this reaction here of sodium hydroxide and hydrofluoric acid. So we've identified that HF is a weak acid, which means the F minus, is it going to be relatively weak or strong? It is going to be relatively strong, right? That opposite relationship. And what that means is we would expect the F minus part here to go through hydrolysis. Yeah. Any questions on that? Now, the other information we could also have that will help us, which is where a lot of people do sort of struggle, is actually writing the equation. So if I know it comes from a weak acid, the F minus should be acting as an acid or a base. It should be acting as a base, right? We have an acid on one side, his partner on the other side is the conjugate base, right? If you have a base on one side, his partner on the other side is the conjugate acid. And that helps me when I'm trying to figure out, all right, I know my F minus should be reacting with water here. And definition of a base is it's going to accept the H plus, right? It's going to send the H plus over there to be accepted. When it does, as we talked about before, you always really make where it comes from, which is why the problem is also very helpful. That's a big hint of that's what should end up on the other side of the reaction there. You actually have part of it. The result of that as well is that we should produce some hydroxide here in this reaction. Any question on how we get to the reaction there? This is obviously the hydrolysis reaction. We also talked about earlier, don't overlook common sense. Obviously, the F minus does not have a hydrogen to give, right? So the only thing it could do is accept it, obviously, in this particular situation. Any questions up to there? Okay, so at this point, we got all of our basic stuff going on here. We can actually get into the calculation part, which is really a nice table. So I'm going to take that equation, I think, maybe if I could stop writing on this thing here. There you go. Maybe it is unhappy with me right now, I think. Yeah. There you go. Do that. All right. So we had our equation, which is our F minus plus our water going to make HF and our OH minus. Now we know a couple of things as well from just simply writing this equation without actually finishing the calculation. My pH should be acidic, basic, or neutral. What should it be, you think? What do I see on the right-hand side of the arrow? I see OH minus. OH minus is basic, yeah? So again, here, without even doing the calculation, laying up the equation, we should know that we should end up with a basic pH. Just like if we did this equation, we ended up with H3O plus on the product side, it should be acidic, right? So it's 0.3, it looks like. So we're going to do our ice table here like normal, 0.3. This is going to be 0 and 0. This will be minus X plus X plus X. This is then going to carry down 0.3 minus X, X, and X. Any questions on the ice table here? Excuse me. We're then going to put this into our equilibrium expression, which would be our HF times OH minus divided by our F minus. This is a Ka, B, C, D, E, F, G. What type of K is this? This is a Kb. Again, I know it's a Kb because I see hydroxide here, which tells me it's basic, and I should definitely be using a Kb value in this particular calculation. Any questions on that? So if you remember earlier, I said these type of problems are historically the ones where they give you the wrong K value. And if you look here, we are not given a Ka value, but we are our Kb value, we're given a Ka value, which is very, very common in these type of problems. So this is where we were going to use our Kw, right? Equals our Ka times our Kb. So we can take our Kw, which is our Ka times our Kb. We can now turn this into a Kb by dividing 1 times 10 to the minus 14 divided by our Ka value, which is 7.2 times 10 to the minus 4. And if we do that there, looks like 1.4 to the minus 11, it looks like. And that is the Kb value that we want to use. And this is a very, very common mistake that people make, is they just use the value given to them in the problem, which it definitely would be incorrect in this case. Any questions up to there? So now that we do have our right value, which let me just rewrite it here so I don't forget, 1.4 times 10 to the minus 11. We could solve like normal. We're going to take our equilibrium line and put it into that expression and solve for X. That gives us X squared divided by 0.3 minus X equal 1.4 times 10 to the minus 11. That is a small value of K. So I'm going to assume X is equal to 0. Remember, you cannot get rid of all the X's as much as you want to. You got to keep something there to solve for. So remember, it's just the X's we're going to subtract or add to. So I'm going to multiply the 0.3 to the other side, and I'm also going to take the square root at the same time just to save some time here. So times it by 0.3, also doing a little square root action on it. That is going to give me something like, I believe X is equal to 2.04 times 10 to the minus 6 in this case. We do want to check it, so we'll divide it by 0.3. We'll times it by 100. excuse me, it looks like we're good. We're not even like 1%. So the assumption is good. Probably in most cases, if you're doing some type of hydrolysis problem like this, your assumption is going to probably be okay. In most cases, I would still obviously take the time and make sure you check, but you'll probably be good to go in pretty much most of the situation. Any questions up to there? So the check here is good. Yay. Now, concentration, but we could clearly see from the table here, it is not the H plus, it is the OH minus concentration, right? So this is actually the OH minus concentration, which means we cannot go directly into the pH equation. We do have to do a little POH action there first, minus the log of 2.04 times 10 to the minus 6 in this case. Going to give us, looks like a POH of 5.69. Now, if at this point, for some reason, you thought that was the pH, understanding that this should be basic should tell you that doesn't look right, right? If that was like the pH value. So these are things you want to think about as you're doing these problems. We could finish it out here by taking the pH is 14 minus that number there. And like an 831 looks like a winner there, 8.31. That is definitely a basic pH and what we would expect, hopefully this to be. Any questions on any of those steps there? So it really is, you know, like a kind of normal ice table that we do. Most people, like I said, do struggle with the writing of the equation and understanding, you know, is it going to be acidic? Is it going to be basic? So there's a lot of clues along the way in a lot of these problems. You want to make sure that you just don't kind of blow by those things. It can really help you a lot. Like I said, because they're nice enough to give you the wrong K value in these problems, oftentimes they'll give you the formula of what it produces in these equations in the actual problem. So, you know, you got almost the whole formula or the equation kind of there in front of you. Any questions on any of those steps there? All right, now I did one, you do one. Yes, all right. Let's calculate the pH of 0.75 molar sodium cyanide. Ka value given. What is the pH? Take a look and see. So we're looking for a pH here of our sodium cyanide. Again, we probably want to start with, you know, is any part of this going to go through hydrolysis? So it does break apart into a sodium and a cyanide there. We've already discussed our sodium, obviously, again, coming from group 1 or 2, not going to go through hydrolysis, really a neutral salt. Probably, again, comes from something like sodium hydroxide. How about the CN minus? Will it go through hydrolysis? CN minus will go through hydrolysis. Again, we do see a Ka given to us for not CN minus, but HCN, which is hydrocyanic acid. And that definitely tells us, because it's a Ka value, it is a weak acid, which means this guy, which is like his conjugate base, should be relatively strong. And again, we would expect the CN minus here to actually react with water. And logic here tells us it doesn't have an H, so it's got to accept the H here. And again, we know it will because it's going to be acting as a base anyway, which means it should be accepting the H plus. That is, again, going to form where it came from, which is a very common theme, which again is also given to you in the problem. And it will also form here some hydroxide. So once again here, the solution should be acidic, basic, or neutral. Again, it should be basic here because we have hydroxide. Also, when we do the calculation, we should again be using a Kb. So once again, we are not given the Kb here, but the Ka. So while we're here, we might as well flip it over to a Kb. So the Kb will be a Kw divided by the Ka, which will be our 1 times 10 to the minus 14, divided by our 6.2 times 10 to the minus 10. That gets us Looks like 1.6 times 10 to the minus 5 in this case. All right, so now we are ready to do our actual problem here. So we're going to take our Cn minus, just going to rewrite it here, H2O. Going to give us some HCN and our hydroxide. So I believe it was 0.75 to begin with, 0 and 0. Change is going to be minus x plus x plus x. And 0.75 minus x, x, and x. This again goes into, as we just said, our KB, which should be our HCN, our OH minus divided by our CN minus. Again, leaving water off of there, and it was 1/6 to the minus 5. Put in our values, gives us x squared divided by 0.75 minus x is equal to 1.6 times 10 to the minus 5. We did good on the first one. Why not try it again here? We're going to assume that x is equal to 0. That reduces that down to x squared divided by 0.75 is equal to 1.6 times 10 to the minus 5. Same math here. We're going to multiply to the other side. I'm also going to take the square root of it at the same time. So that would get us times 0.75 and a little square rootage. Not that. Try that again. 1.6 to the minus 5 times 0.75. Now square root it. Looks like we do get an x value of maybe 3.5 times 10 to the minus 3 in this case. We'll check it by dividing by 0.75 and times it by 100, and it's like 0.4%. So we are good here in terms of our check. Any questions up to that point? Once again, we want to make sure we go back to our ice table and really check what we're dealing with. And we are dealing with hydroxide here. So that means that the concentration of hydroxide is 3.5 times 10 to the minus 3 molar. Means the POH first would be minus the log of 3.5 to the minus 5. Gets us like a 4.46 here. So just make sure here my calculator didn't mess up. 3.45 to the minus 3. Yes, that's why it didn't look right to me. I wrote it right here. Like, wait, something didn't look right. Let's try that again. Thank you. Like, yep. Copy it over right, apparently, as well. That's probably helpful. All right, let's try that again. At least I knew it didn't look right to me. All right, so 2.46 seems a little bit better. All right, well, 3.5, you know, it's kind of close. So now our pH, thank you, will be our 14 minus 2.46 gets us 1154. That sounds a little bit better, I think. That's good. I'm not sure how it became 5 as it went that way, but you know, it happens. Yes. Yeah, so you're asking how to do the check? Yeah, so you take the x value you got, so I'll just write it here, 3.5 times 10 to the minus 3. And basically, you'll divide it by what you're going to subtract that from. So you'll divide that by 0.75 and times it by 100%. And I think in this case, it's like 0.4% or something like that. So as long as it's under 5, yeah. Other questions on that? So again, here it does make sense, even more sense that we got the right number in there, that it is still basic. I think I ended up basic anyways, but it should be 1154, which is basic because it again is generating our hydroxide. Any questions on any of that there? Let's see what we got going on here. Let us maybe. I want to try one more. What is the pH of a 0.35 molar ammonium chloride solution if the Kb value for NH3 is 1.8 times 10 to the minus 5? Okay, let's take a look and see. So again, we're going to be focusing on the salt, which is the ammonium chloride here. When it obviously breaks apart, we get a couple of things. We get some ammonium and we get some chloride here. How about let's start with the chloride. Will the chloride go through hydrolysis? It will not, because it most likely came from hydrochloric acid, right? Which is a strong acid, which means it's going to be relatively weak and be neutral. How about the NH4 plus here? It will. Again, the other piece of helpful information is over here. I see a Kb value associated with that guy right there that looks very much like it, but not exactly it. So that tells me this is a weak base, which means this partner over here is going to be like the conjugate acid and be relatively strong and actually go through hydrolysis. So the reaction that we should be looking at here would be NH4 plus reacting with the water. Again, understanding that the NH3 is a base, which means NH4 will act as an acid when it reacts with water. That tells me that I would expect it to donate the H plus over to the other side as it's acting as an acid. The result of that is, just like previously, we will make where it actually comes from, which again is also in the problem in case you need it. And more importantly here, we're going to make a little H3O plus. So again, without doing the calculation, we should expect the pH here to be, should be acidic because we are producing H3O plus. So again, we want to kind of think about these things as we're doing these problems. It helps us make sure we didn't screw up along the way with the calculation part. So let's do the ice table here, which is 0.35. This would be 0 and 0. This will be a minus x plus x plus x situation, giving us 0.35 minus x, x, and x. Any questions on the ice table part of it? We can go into our K expression here, which is our NH3, our H3O plus, and our NH4 plus. This is going to be a KABC. This is going to be a KA that we need. Again, this is what the equation is going to help us truly understand. Should be acidic, and again, should be using a KA in this situation. So once again, here we do need to kind of switch it over there to a KA in this case, which would be 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, 5.6 times 10 to the minus 10, perhaps. Yes. Putting our values in gives us x squared divided by 0.35 minus x equaling our Ka value in this case. Same math, we're going to multiply to the other side. I'm also going to assume that x is equal to 0 here. So I'm going to get rid of that x. So we're going to multiply to the other side and then take a square root of it. If I could grab my calculator here. So 0.35 times 5.6 to the minus 10, then a little square root, and gives us an x value of 0.000014. Again, to check it, we would take that number and divide it by 0.35 and times it by 100, and it's like 0.004%. So we are good on that check in this case. Yeah. Any questions up to there? Now, unlike the previous ones we did there, when we actually do look at our ice table, if we're not sure, we see that x in this case actually does equal the H3O plus value, which means that this is really the H plus concentration, right? Those things are interchangeable, which actually means in this case, we can go directly into the pH, and the pH here would be minus the log of what we got going on there, however many zeros. and minus the log of 0.000014. Looks like a 4.85 on our pH. That is acidic, like we would expect it to be. So all that makes sense. Yeah. Any questions on salts or how to work these problems? Again, two major stumbling points for a lot of people: writing the equation correctly and using the wrong K value. So these are two very common places where people really do make mistakes on these things. Any questions on any of that there? All right, so that should be salts, I think. All right, and that's just a picture of, I think, what we talked about earlier about the aluminum. And again, just how regular water comes off and plucks off a hydrogen, makes our H3O plus. So as we talked about this morning and last time as well, remember, again, that's sort of another way that you could technically have a salt, and it's usually transition metals that have a relatively larger positive charge, like +2, +3, and usually is sort of associated with water. And again, one of the waters that's associated with those ions that are floating around will lose a hydrogen and basically produce H3O plus in the solution, and it will be acidic. So if you see some type of metal that goes through hydrolysis, it should end up sort of acidic and produce H3O plus pretty much all the time. Now, up until this point, we've talked about salts that only really one part of the salt, for example, goes through hydrolysis. It is possible, for example, maybe if you had something like, say, ammonium fluoride, for example. If we take ammonium fluoride, that is going to give us two options, which is NH4 plus and F minus, right? So as we just saw, the NH4 plus will go through hydrolysis, right? And the F minus will also go through hydrolysis, right? As we saw earlier as well. So it is potentially possible that you could end up with a salt where actually both parts will go through a hydrolysis reaction, as opposed to, you know, what we've been seeing, that just like really one part of it actually goes through it. So in those situations, we do a similar thing to what we talked about today. We actually compare the Ka value to the Kb value to help us determine sort of which way the reaction will happen. If you do sort of the long version of that calculation, it's quite complicated having both things happen at once. So usually we sort of pick one or the other. So if you look at the Kb value for the anion, the negative guy, which is greater than the Ka for the positive guy, you would expect it to be basic, and you would do sort of the basic calculation for that particular problem. If the Kb for the anion is less than the Ka for the cation, then basically it's going to do the acidic approach here, and you would do the acidic reaction. And if they're approximately the same, you would expect it to be pretty much neutral in that case. So kind of a little bit similar to what we were talking about earlier, but in this case, both parts of the salt's able to go through hydrolysis. You would again compare the Ka to the Kb, and whichever one's larger would be sort of the approach that you would take there. And that's what we sort of see here on the chart on the bottom there. Anything that comes from a strong base and a strong acid, the pH will be neutral. Anything that again comes from a strong base and the anion is a weak acid will go through hydrolysis and become basic. And anything that really is a strong acid and it comes from a weak base will end up being acidic. And again, here's some more examples of guys that actually could go both ways. We would want to compare again the Ka to the Kb values to determine which way it will actually go. And then lastly, our sort of charged metals here. And again, those guys will always be acidic. Really, the water part of it is what's producing an H3O plus. Any questions on salts? Okay. Now, this is some oxides. Oxides are obviously elements that contain oxygen. when we take certain oxides on the periodic table and react it with water is where we produce either kind of bases or acids. So as we talked about a number of times over here in group 1 and group 2, we got our guys that pretty much, if you lay up some water with like sodium oxide or potassium oxide, you're going to produce like sodium hydroxide, potassium hydroxide. So a lot of our bases come from over here. And these guys are sometimes referred to as basic oxides for that reason. If you add water to them, you'll pretty much get your strong base that will happen. Where our kind of nonmetals are on this side here, kind of nonmetals that have oxygen involved, they typically is where our acids come from. So if you think about something like CO2 in some water, that makes carbonic acid. And that's where a lot of acids sort of come from, is on that side. And then we do have stuff that kind of could go both ways. These are amphoteric guys. Also why we don't include beryllium when we talk about group 1 and group 2, because it can kind of go both ways. But amphoteric oxides, again, can either act as an acid or a base. So kind of like what we've been talking about, left-hand side of the periodic table, kind of where bases come from, upper right non-metal, kind of where acids are generated from when they do react with water. They obviously have oxygens in there. Any questions on that there? So we talked about a couple of definitions of acid and bases, and there's a third sort of definition that is sometimes used. So we've talked about the Arrhenius definition of an acid and base, which is something that produces H+ in water. Bronsted-Lowry definition is a proton donor. Our good friend Lewis didn't want to be left out. Yes. When we think about Lewis, we think about Lewis structures. Lewis structures involve what type of things? Electrons. So the definition of an acid and base here, our Lewis acid and base, does involve electrons. A Lewis acid is something that will accept a pair of electrons, while a Lewis base is something that will pretty much donate a pair of electrons. So electrons to be accepted or donated, or really donated, usually come from things that have like extra electrons, if you will. Those are typically things that are negatively charged. That's how things become negatively charged, right? They gain extra electrons. And also things that have non-bonding electrons in sort of a polar situation where you have unequal distribution of electrons is where that happens. So here's our hydroxide, which in this case, would be acting as the base, donating some electrons over to the H+. By the way, if something is positively charged, it means it has lost electrons, right? And are electron deficient, which is why it will accept electrons, right? It's willing to do that. Same thing here. This is ammonia, which is a polar molecule. It's got those non-bonding electrons that can transfer over there. Again, making this our Lewis base. And obviously our H+ are acid in each situation. These are also obviously the exact same results you get if you look at it in the Bronsted-Lowry definition, H+ being donated, acid, other guy accepting it being the base. So exact same result in terms of what's an acid or base. But Bronsted-Lowry looks at protons being donated and accepted, and Lewis acids look at electrons being donated and accepted, but the end result is the same sort of classification in either way. This is the base and this is the acid. And same thing on the bottom there. This guy would donate the H+, making it the acid. This guy would accept the H+, which would make it the base in the Bronsted-Lowry definition. The sort of advantage of Lewis acid and bases, and we will see Lewis acid and bases in a later chapter in the semester, but it could actually be used to kind of apply acid-base chemistry to something that does not involve H+ being transferred. So if we look at something like this guy, there's no H+ here, but again, this guy has a pair of electrons to donate to boron. You might remember boron is an exception to the octet rule. It has an incomplete octet, which means it has less than 8 electrons, which means it's also deficient in electrons and willing to accept those electrons. And in this particular situation here, whoops, come back, maybe. This would obviously be our base, and this would be our acid in this case, as the boron accepting those electrons. So we definitely will see Lewis bases a lot later on when we talk about transition metal chemistry and complex ions. It's all about really the electrons kind of being moved around in that situation. Any question on Lewis acid bases? So a couple things to remember with that involving electrons, not protons, and it is actually opposite of Bronsted-Lowry in terms of accepting and donating in terms of the electrons. All right, so what we're going to talk about here is, again, polyprotic acids. So as we've talked about before, when an acid will sort of lose a hydrogen, it will lose it one at a time. So again, if it has multiple hydrogens to give, a diprotic or triprotic acid, each hydrogen will basically come off one at a time. So as we saw earlier as well today, we talked about like phosphoric acid, for example. Again, the first thing that's going to happen is that first H plus will come off and we will be left with H2PO4 minus. This is a Ka1 value for that process, which happens to be like right there on this table. Now, the second thing what happen is the result of that sort of reaction will then go and lose the next hydrogen. And we will get to HPO4 2 minus. And that will give us our Ka2 value, which is right there. And lastly here, that last guy will drop the last hydrogen off. And that would be represented by Ka3, which is this last value here. Again, for each hydrogen that comes off in sort of a polyprotic situation, if it's a weak acid, you will have a Ka value for each of those sort of hydrogens that come off. Is it easier to remove the first hydrogen or the last one? Which one do you think would be the easiest to remove? It is the first one. We remove the first one for something that's neutral, right? And after we remove it, we now become a little bit negative, right? Which is going to make it harder to pull off a positive guy, right? So it gets harder to do that. It gets even harder down here, right? Because now we got like a -2 charge happening there. So it's going to be harder to push that out. And we do see that if we compare the values here, the Ka value, Ka1 is 10 to the -3 versus the very last one there, that's like to the minus whatever it is there, 13. So it's a much smaller K value at the end for the third step than it is for the first step. When we have a very small K value, that means we mainly have reactants or products. Small K value means mainly reactants, yes, products over reactants. So what that means is when we get to the very small Ka3 value here, we mainly have reactants, and on the reactant side, not a lot of that coming off, right? So we're mainly over here on the left-hand side, which means we're not going to lose a tremendous amount of H plus, as opposed to the first step, which is much larger, which means we would have more products in that first step, right? And a lot more of the H plus would come off. And we see that trend for all kinds of polyprotic acids here. Ka1 value is always larger than the Ka2 value. Again, it gets significantly harder to continue to remove those guys. So we could use these values like we did earlier for like salt sort of purposes, but we could also use these values to calculate the pH and everybody that's there in a polyprotic acid situation. So let's take a look at one of those type of deals. We'll come back to that in just a second here. So let's say we took this problem here, which is essentially we want to calculate everybody that's involved there in the solution, everybody that went for a swim, starting with a 5 molar phosphoric acid solution. This is our Ka1, which again represents the first hydrogen that comes off. This is our Ka2, which represents the second hydrogen that comes off. And lastly, our Ka3 there, that represents our third hydrogen that comes off in this particular case. All right, so we basically want to know what the concentration of H3PO4 is at equilibrium, H2PO4 minus, HPO4 2 minus. phosphate, the H plus, and the pH, like everything you ever wanted to know or don't want to know in this case. What this means is, since we actually have to go all the way down to phosphate, we are going to have to get all the way down to this equation at some point, right? So we're going to have to use each of these guys along the way. So we might as well start with the first step here, which is the first step that's going to happen is we're going to lose that first H plus that's going to come off. So we would start with a normalized table, starting with our acid there. And let's do that. So the very first thing that's going to happen is our phosphoric acid will drop off that first H plus. Give us H2PO4 minus. This is going to be our Ka1, which was 7.5 to the minus 3. All right, so we're going to do an ice table, and originally, I think I wrote 5 molar on that, yeah? Okay, so we have an initial concentration of 5. Everything else here is going to be zeros. We're going to do our change, which like normal will be minus x plus x plus x. That means at equilibrium, we got 5 minus x, x and x. So starting out here is just going to be a regular kind of roll through here. We're going to put this into our Ka1 expression, which would be our H plus times our H2PO4 minus, divided by our phosphoric acid, and that obviously equals our value there of 7.5 times 10 to the minus 3. Like normal, we're going to take our equilibrium line and put it in there. That's going to give us an x squared divided by 5 minus x equals 7.5 times 10 to the minus 3. I'm going to assume that x is equal to 0 here and hope for the best. So that is going to be x squared divided by 5 equals 7.5 times 10 to the minus 3. Normal math, going to multiply to the other side and take the square root here. So 7.5 to the minus 3 times 5 and some square rootage. Going to give me an x value here of 0.194. We do want to check it, so we're going to take 0.194 divided by 5 times it by 100, and it is 3.9%. Yay. That's probably why I changed it. Yes. For years, I did one where I had to go quadratic. I didn't feel like quadratic. So that is good. The check is good here. And that means that after doing this very first ice table with the very first hydrogen that comes off, we actually have a number of answers that we're looking for. So we're looking for everybody's concentration. So off of this very first ice table here, we were able to determine that obviously the concentration of H plus would equal X, which would be 0.194 molar. We also know that the concentration of H2PO4 minus also equals X, which would be 0.194 molar. And we know that the concentration of H3PO4 at equilibrium equals 5 minus X, which would be 5 minus 0.194. Looks like I will call it 4.81. First off, any questions on that there? So off of this very first table here, we pretty much were able to knock off this guy, I believe this guy, and this guy from the very first table. Problem is, though, we need to get into these guys, so we then need to kind of go and do the second step that's going to happen, because the question is pretty much asking about everybody that's going on there. Any questions on that so far? So the next thing that's going to happen is the second hydrogen is going to pretty much come off here. So let's do that part here. So the second step is, remember now that this guy here will drop off the second hydrogen. And because this is the second hydrogen, this would be our Ka2 value that we saw in the problem. And that was 6.2 to the minus 8, I believe. Any questions on that? So the question, though, is where do I find my initial concentrations from? What do you think? It would come from the previous table, right? So there we go. So our equilibrium concentrations from the first table, right, is going to be our initial concentrations on the second table. So that means that we have 0.194 for our HPO4 minus. So 0.194. How about the H plus? Do we have some of that from the first table? We do. It also is 0.194. And we obviously don't have any of this guy at the end, right? So we do actually have those two. And again, they come from the equilibrium line from the previous table. And obviously that's going to carry over to our initial. The rest of the ice table here is going to be the same, minus x plus x plus x, which means at equilibrium 0.194 minus x, 0.194. Remember, this is actually plus x here, and that is going to be x. Any questions on the ice table here? This is going to go into our Ka2 expression, which is our H plus, our HPO4 2 minus, divided by our H2PO4 minus, and that will equal 6.2 times 10 to the minus 8. Putting in our values gives us 0.194 plus x up on top times x divided by 0.194 minus x on the bottom. And that will equal 6.2 times 10 to the minus 8. Might as well continue my streak of assumptions here and assume that x is equal to 0. That's going to get rid of all the x's except for the x that's by itself. We don't get rid of the x by itself because any change there, starting from 0, is significant, right? So if you start at 0 and you make like anything, that's a pretty big change. So that's why obviously we can't get rid of it. So that's going to reduce this down to 0.194 times x divided by 0.194 is equal to 6.2 times 10 to the minus 8. I could do this math, I think. That cancels. And that will give me that x is equal to 6.2 times 10 to the minus 8 in this case. Any questions on that there? Do a little checking, divide that by 0.194, times it by 100, and you're like 0.0003%. So you are good on the check here. So from the second table, we are able to see that the concentration of one of the things we're looking for, which is this guy right here, would be 6.2 times 10 to the minus 8 molar. Now, what happens to my H plus concentration at this point? If I take 0.194 and add it to this number, what number do I end up with? I basically end up with 0.194, not very much, right? And same thing here, if you took that x and put it back into here and you subtracted it, 0.194 from it, you will still end up with 0.194. So those guys really aren't changing all that much. They're still hanging out basically the same, but we now have found our H2PO4 here, which is this guy that we're looking for. So we're down to just looking for the most part, our phosphate. And obviously, when we look at our equations for each of the steps, the only step that involves phosphate is the third step. So that is where we're going to go next. We're going to do an ice table with the third step there, which is, so let's do that there. So on our third step, it's going to be our HPO4 2 minus, going to drop the last hydrogen here, going to then get us to phosphate, which is kind of what we're looking for. And this would be our Ka3, which is 4.8 times 10 to the minus 13. Again, just like previously, our initial concentrations are going to come from the equilibrium of the last table. So last table, we have 6.2 times 10 to the minus 8 for this guy, 6.2 times 10 to the minus 8. How about hydrogen? Do we still have hydrogen there? We do, and it is still the same concentration really that it kind of started with there, which is 0.194 in this case. And this would be 0. Again, now we're going to do minus x plus x plus x, going to get us to 6.2 times 10 to the minus 8 minus x, 0.194 plus x, and x going into our Ka3 expression here, our H plus, our phosphate, our HPO4 2 minus, 4.8 times 10 to the minus 13. Putting our values in, we got 0.194 plus x times x divided by 6.2 times 10 to the minus 8 minus x, and that will equal 4.8 times 10 to the minus 13. I'm not going to stop now. We'll go assume x is equal to 0 one more time for good measure here. 0.194 up on top times x divided by 6.2 times 10 to the minus 8, or 4.8 times 10 to the minus 13. We're going to multiply that to the other side and then divide by 0.194. That gets us 6.2 to the minus 8 divided by 0.194 gets us an x value of 1.5 times 10 to the minus 19 in this case. Again, we could check it by dividing by either number, and you are definitely good no matter which number that you divide by to check it. As we can see from this particular table, that is going to be our concentration here of phosphate, which is what we're looking for. So the concentration of phosphate is 1.5 times 10 to the minus 19 molar. Just like we saw in the previous table, if I take that 1.5 times 10 to the minus 19 and put it in here, I am still going to end up at 0.194. And if I put it into here, I will still end up at 6.2 times 10 to the minus 8. Any questions on any of that there? The last thing that we were going to calculate is really the pH, right? So that's the only thing we haven't calculated yet. But let's talk about the H plus concentration as we went from beginning to end here. So at the very first step, we took off 0.194 molar of H plus came off, right? At the second step, we basically took off 6.2 times 10 to the minus 8 of H plus, basically, right? Is that a lot? It's a lot less, right? A lot less came off in the second step. When we got to the third step for the H plus, essentially we took off that much, which is to the minus 19, which is even less. So this is what we were talking about earlier. As we go from like the first hydrogen to the second one, it gets much more difficult for the H plus to come off as reflected with the Ka value. And as we go from the second, in this case, to the third hydrogen, even harder to remove that third hydrogen. As we can see with the actual numbers here, not very much came off. That's the change part, which is how much actually came off. And it's a very, very small amount. So good news, bad news in a problem like this, if you are not asked like this problem was, what is everybody's concentration? But you were simply just asked, what is the pH of this acid? You could probably safely in a polyprotic acid use the H plus from the very first table, right? Because it pretty much did not change all the way through. So again, if you're not asked to calculate everything, you don't have to go through all the steps, obviously. If you are, then you obviously do, like we did in this problem. But in most cases, if it's just a straight polyprotic acid and you just want to calculate the pH, you are pretty safe just to use the very first H plus that comes off. That in pretty much all cases will be the majority of the H plus that comes off in that solution. So that means we can just go from the first one or any of them because they really haven't changed and calculate our pH of this acid, which is going to be a small pH here, I think. Log of 0.194, like a very acidic 0.71 when you make up numbers. There we go, 0.71 pH. That definitely is acidic, I would say, since 0 is quite acidic. Yeah. So this demonstrates a couple of things that we've talked about in terms of the Ka value. We can actually see the numbers here that as you continuously try to take off that H+, it gets more difficult, and it really doesn't come off all that much. Majority of the H+ in a polyprotic acid will come off in that first step. And like I said, if it's just a problem of calculating pH, you're probably in good shape just to do it off of that first one. And again, clearly, if you need to calculate everything, you got to go through all the steps. Any questions on how to deal with polyprotic acids? Okay, so we're gonna lay it up here, a couple